Let me get some of this down here. Chat window open. All right, I'll give another little, maybe half a minute to make sure, give people a chance to show up. All right, hi, welcome back. Hi, nice to see your face, Stephen. So, what do you want to talk about today? Oh, I have a good idea. Let's talk about surface integrals. That's 13.7. So this is a short, Wednesdays are short classes, so I just want to lunge right into it so we can take advantage of the time we have. Section 13.7 was about surface integrals. And last time, remember, we had maybe I should ask, how's everybody? Does anyone have a question before I get into it? No, you're just too excited to do the math. I get it. Okay, so last time we realized that there was two types of surface integrals. There was surface integrals of real valued functions and surface integrals of vector fields. And we did the surface integrals of real valued functions pretty quickly. We moved on. Surface integrals of vector fields, that's where it's at. That's flux. And we managed to do an example right before we ended, but I think we benefit from another example. Does anyone agree with that? Yes, we have some nods. Okay, so let's just try another example. Oops. How about this? Integrate this vector field. F of x, y, z equals x, z, e to the y, x, z, negative x, z, e to the y, z, over the part of the plane x plus y plus z equals 1 in the first octant with downward orientation. All right, so we have our vector field, we have our surface. So what, remind me, what are the 4 types of surfaces that we need to know how to parameterize?
Round things.
Round things, things with round cross sections. Yes, what else?
Planes.
Spheres.
Planes, spheres, oh, we got 2 of them, and one more thing.
Function.
Graphs of functions, yeah, okay. So there's no doubt that this thing's a plane. It says plane right here. And so you might think, let's parameterize that as a plane. Well, that's totally fine to do. Since this is already given to you as a formula, it'll actually be even shorter to treat it as a graph of a function. But either way that you want to do it is totally fine. I'm going to do it as graph of functions to show you all the varieties. So how can I express this as a function? Oh, maybe I should have said this. Why did I ask you what there was to parameterize? Because the first thing you always do when you do a surface integral is you got to parameterize the thing. So we're going to parameterize the plane, the portion of the plane. Let's see, maybe we need a picture of that. So what's this going to look like? So I have this plane x plus y plus z equals 1. Well, I'm going to think of the x and the y and the z intercepts. So the x-intercept is when y and z are 0. And if y and z are 0, then x is 1. But also, if x and y are 0, then z is 1. And if x and z are 0, then y is 1. So it's a plane that goes through those 3 points. It's going to sort of cut, it's going to cut the corner off, right? But we only want the part of the plane in the first octant, so we only get sort of this. that portion of the plane. Okay, so the thinking of this as a function, the plane is, let's solve for z. Z equals 1 minus x minus y. So our parameterization as a function, that's going to be confusing. Our parameterization as a function is, well, x and y are the parameters. Those are the independent variables. And then so x is x, y is y, and z is whatever the function tells us it has to be. So z is 1 minus x minus y. Now for setting up the bounds, let's think about what x and y values give us points on this plane. So the x and y values that do that are the x and y values down here on the floor. Does that make sense? For every x and y value there, when I plug that in to get a z value, I get 1 point on that little triangular patch of plane. Is anybody following this so far? A little bit? Does anyone want to ask a question? Okay, not quite yet. All right, so let's think about if I want to set up the bounds, if I want to have the bounds for x and y, let me just focus more carefully on what it looks like for x and y. So we've got this region right here. That's one, and then this is where the integration is taking place over. So we want to set up the bounds based on that picture. So then what are the bounds for x and the bounds for y? Can anyone tell me?
You could do y goes from 0 to 1 minus x,
Oh, so
and
good.
then x goes from 0 to 1.
So good, that's right. So in the last class, somebody suggested, hey, look, y goes from 0 to 1 and x goes from 0 to 1. Well, in some sense that's true, but if we did that, then we would really just get this whole square, right? And we didn't mean all of that. We really just meant the y values going from here to some function of x. And Philip was right. What is that function of x? Well, first of all, you can see that you know, this has y-intercept 1 and slope -1, so y equals 1 minus x. But if you didn't like thinking of it that way, you could also say, well, it's also where the plane hits the xy plane, and that's when z is 0. And if I look at this formula with z is 0, I get the same thing. And anyways, Philip's exactly right. The y value is going to go from 0 to 1 minus x, and the x value is going to go from 0 to 1. This is where all your practice of setting up double integrals over regions is going to pay off, right? Now, now we sort of feel comfortable with coming up with bounds based on these. All right, parameterize, awesome. What's the next thing that we have to do?
Find, I was going to say find r sub x and r sub y.
Good, find r sub x and r sub y and take their cross product, absolutely. So let's find r sub x cross r sub y. So r sub x, so again, I'm looking right here. So partial derivative of this with respect to x is 1, 0, -1. Partial with respect to y is 0, 1, -1. Now I take the cross product. So rx cross ry 1, 0, -1, 0, 1, -1. I'm going to repeat these. Okay, so let's see, the forward direction for I is 0, and the backward direction is -1. So I have 0 minus a -1, so that's +1. Forward direction for J is 0, the backward direction is -1, so I've got 0 minus a -1 again. Forward direction for K is 1, backward direction is 0. So I've got 1, 1, 1. We finished the last problem before the end of class, so I don't have the notes from that up. But if you look back at your notes from the previous problem, That was when we were doing a surface integral over the sphere. The cross product we had was just a disaster of phis and thetas. You remember that? So it had a whole bunch of variables in it. This one has 1, 1, 1. This one's a constant. Does that make any sense? Why would this be a constant? But what does this even mean? Rx cross Ry, what does that mean with respect to the surface that we're thinking about? And that surface, hope this doesn't blow the picture, is this green triangle that's supposed to be sitting in front of the origin. What does Rx cross Ry have to do with that surface?
It's a perpendicular vector from that surface.
Excellent, that's right. It's a
Where, like,
perpendicular
all
vector
the
to that
lines
surface.
are up.
It's a normal. Does it make sense that I get that's a constant? It doesn't have any variables in it?
Because the sphere is like round and like kind of roly.
Sphere is kind of roly. So so wherever you are, the normal vector is going to change depending on wherever you are, and so you expect it's going to change depending on theta. It's going to change depending on phi. So we're not surprised that there's variables in that formula. But for the plane, however the plane's oriented, you move the the normal vector is always going to be pointing in the same direction. So it's not surprising that we got a constant. That makes sense to us. All right, so there's the cross product. Now what?
The magnitude.
Do we take the magnitude? So the magnitude we needed when we were doing the surface integral of a real valued function. We took the value, the number, which is the real valued function, multiplied it by the number, which was the magnitude. Whenever we do the surface integral of a vector field, we're going to do the dot product of a vector with a vector. So we actually don't need the magnitude in this case. Yeah, what next? Check the orientation. So good. That's right, Javi. So let's check the orientation. All right, so let's look. What did they ask for? In the problem, they asked for the downward orientation. What does downward mean? So in terms of, if I'm looking at a vector, I've got the 3 components of a vector, and I'm going to tell you that vector is pointing in the downward direction. What part of that vector are you going to look at? How can we sort of quantify that? So I would think of any of these as being downward. I mean, this is straight downward, but any of these are sort of the downward direction. What is it about downward pointing things? If I look at a vector, what am I going to look at to see whether it's downward?
Z is minor, negative.
Yeah, that's right. The z value is negative. So downward orientation, in other words, negative z value. Okay, but let's look at ours. Our parameterization gives a normal of 1, 1, 1, which has positive z value. Okay, those aren't in agreement. So this parameterization is orientation reversing. Okay, that's fine. Doesn't hurt us. We just needed to know one way or the other. Last thing, now we're in a position that we can evaluate the integral. Okay, let's see. We're going to do the double integral over the surface, vector field dot ds. And the way we evaluate that is, well, we care everything has to be on the surface. So we care what happens at the parameterization. So everything's got to be in terms of the parameters x and y. So we want f to be evaluated at the parameterization. We're going to dot that with Rx cross Ry. And then I would say dx dy, but actually think about how we set up this, our parameterization, our bounds. Y goes from 0 to a function, so y should be the inside variable. So let's put the y on the inside, dy dx. So y goes from 0, sorry I have to squish this in, to 1 minus x, and x goes from 0 to 1. All right, bunch of stuff to plug in now. So 0 to 1, 0 to 1 minus x, f of, well, what's the parameterization? We go back and look, the parameterization is r of xy equals xy 1 minus x minus y. And then Rx cross Ry, remember that one's 1, 1, 1. Are we ready to take the dot product? Is that what's next?
Need to substitute the and the f.
Yeah, that's right. You have to plug it into F first. Sometimes students will see it looks like there's a vector here and a vector here, and they want to dot these. But remember, this is the input into a function. So you have to plug it into F first before we can take the dot product. So, okay, well, let's look at what the vector field says. The vector field is this guy. So it's x z e to the y minus x z e to the y z. So first, third, e to the middle. So first, x, z, e to the y, comma, minus x, z, e to the y, comma, z. Dotted with 1, 1, 1. Okay, I picked this problem. Well, it's a good problem anyways, but I kind of picked it on purpose because the integrating kind of drops away and we don't really have to worry about that too much. The hard part about this right now, the new part, is what are all the steps? How do you set it up? What do you plug in where? And then the integral, well, we're getting good at those. So if I do this dot product, that's fine. I've got this times 1, and then this times 1. Hey, these guys are going to cancel each other out. So let's see, I'm going to have x times 1 minus x minus y e to the y minus x times 1 minus x minus y e to the y plus 1 minus x minus y dy dx. So I'm tempted to stop right here. Is there anybody who would like me to finish this? Doesn't feel comfortable with doing this integral? I think this is sort of something we're past by now. But if somebody's feeling rusty, I don't mind doing it. What do you think? Oh, we good? Okay, so I'm just gonna say dot 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 finish the interval, the integral. All right, look at all these steps that we had just to get the integral set up. What questions did this bring up? Is there any thing that I could explain again?
Did we need a negative sign for the? Oh yeah, someone actually pointed it out in the chat.
You're totally
Negative sign
right.
for integral solving.
You saying that? I can't see you saying that. Who was that who just said that?
Aima, but someone in the chat also pointed out the same thing.
Oh, okay, yeah, totally. You're exactly right, Aima and Roger. You're exactly right, and I just forgot to put it, so thank you for calling that out. So since it's orientation reversing, there should be a negative sign here. Good. So negatives for all these, etc. Okay, good, awesome. What else? Okay, so that's surface integrals. And I'd like to say we're not really done with surface integrals. The whole rest of the semester is about surface integrals. And we're just gonna need to do more practice. And lucky for you, we've got a lot of things we can practice with. I forgot to share the last class, but maybe I'll show you both tomorrow. I've got this whole fun pack of surface integrals that you can do, and no end of fun for that. So it's going to give you a lot of practice. But I think we understand maybe what all the steps are, and we just have to practice all the steps. So that's all I'm going to say specifically about evaluating surface integrals. And now I'm going to keep going with this program that I told you we were going to follow, which was the same thing we did for line integrals, right? First thing we did was figure out how to parameterize. We talked about parameterizing surfaces. We talked about some like basic surface integral, like for surface area. Then we talked about the two real types of surface integrals, which are surface integrals of vector fields and of real valued functions. And then where we're going to go from here is now we're going to start talking about theorems. There's two really awesome theorems that are related to the surface integrals. And what are the benefits of the theorems? Well, two good things about the theorems. One is sometimes it makes a computation easier, and who doesn't like that? Sometimes you can swap a horrible computation for an easy computation, and or even one that's not even possible for one that's possible, and it's good to know how to do that. But another good reason to care about the theorems is, we've thought about so many things this semester. We've got, oh my God, we've got cross product, we have dot product, vectors anyways, we've got vector fields, surfaces, parameterizations, what else? Oh, double integrals, we're gonna have triple integrals, all these pieces, curl, div, all these pieces, and it helps us understand these pieces whenever we see different ways that they're related to one another. And that's what these theorems do, is they say, hey, this idea is related to this idea. And so both the next two theorems, which are the last two sections from the class, are Stokes' theorem, the divergence theorem, and they are just super cool. They're super cool because, they make computations better, but they're also super cool because they connect these ideas in a really beautiful way. So coming up, we're going to be doing theorems from now on. And I just want to remind everybody, so a couple people forgot on the exam, so I'm just going to remind everybody again, whenever you use a theorem, in this class, in the computation, you must, what are the things? Remember there were some things that you had to do in order to use a theorem. I put them on the exam last time and in the notes. Can anybody remember any of them?
Hypotheses, or like recall the hypotheses.
There you go, that's right. Know what the hypotheses are. I'm gonna put it in one piece. I'm gonna say, state and check the hypotheses. So you need to know what they are and also check whether they satisfy. If you want to put that in 2 steps or 1 step, it doesn't matter. But we're gonna state and check hypotheses, or the conditions. Awesome. That's really the most important one of all the steps to make sure. Otherwise, you don't know if you can use the theorem or not. And then Phil says, name of the theorem. Absolutely. If you're going to use a theorem, tell me what theorem it is that you're using. So I'm going to put that first, name the theorem. And then Philip also says, show where it's used or sued, right? So show where it's used. I'm going to put that as number 4, show where in the computation you use the theorem. And then the third piece, I can't really do the 4th piece without the 3rd piece. So the 3rd piece is, don't start at the other end of the theorem, start with what they asked for. If they asked for a double integral, start with a double integral. Maybe you apply a theorem and replace it with a single integral, that's fine. But don't start with a single integral, because I'd be like, wait a minute, I asked you for a double integral. This doesn't make any sense to me. And plus, then you wouldn't have a chance to show me where in the computation you use the theorem. So we're going to start with the computation asked for in the problem. Okay, and then they'll give us an opportunity to show where we use the theorem when we convert that computation to another computation, which we hope is going to be easier. All right, with all that background, let's talk about Stokes' theorem. That's section 13.8. Okay, here's what Stokes' theorem says. Stokes' theorem says this. So let F be a vector field from R3 to R3. And let D be a surface. Leave some space because I'm going to add some conditions in here, but not quite yet. So just leave a little bit of space. Then I'm going to say then the double integral over D of the curl of F dot ds is equal to something. Well, I'm going to take some time to unpack what it's equal to. Maybe I should point out, why am I leaving a space rather than just telling you what the conditions are off the top before you even get into it? Here's the reason. For this particular theorem, the conditions are kind of built into the statement of the, into the formula. And if you don't think carefully, you miss those conditions because you're not focused on all the subtle details in the formula. So I'm going to call them out. I'm going to name them and call them out so that it doesn't get lost. That's all. But it's not going to help unless we see what the formula is. So we're just going to put that off for a second. So let's think about what all these, let's explore this left-hand side. So, so note, leave a little bit more space maybe. Let's think about this left-hand side. So what about curl of F? I have a vector field and I want to think about the curl. What kind of object is the curl? Is that a vector? Is it a scalar? Is it a function? Like what kind of thing is it?
It's a vector.
It's a vector, absolutely. And the vector has a direction and a magnitude. What's the direction of the curl vector? What does it have to do with F?
Isn't it like where it's rotating?
Yeah, it's the axis around which it's rotating. Absolutely. So curl of F equals axis of rotation of the vector field F. Well, you know, curl of F isn't a number. It's not a constant vector is what I meant. It can change. So there could be some rotation over here like this, and the axis of rotation would be here, but maybe here the rotation is like this, and then maybe here there's no rotation at all, so the axis would just be the zero vector, or, you know, there's it can change. But in any case, at any given point, the curl is the axis of rotation of the vector field. And also, you know, there's more stuff like the direction of the curl vector determines whether the rotation is going this way or it's going this way by the right-hand rule. The magnitude of the curl vector tells you some stuff about the size patch of the surface it represents. That's fine. The thing I care about is that it's giving us the axis of rotation. And then what about ds? What is that? What does that give us? So I've got a surface. ds, that's like rx cross ry or ru cross rv. What's that vector look like?
Is that like a small area?
A small, oh yeah, if it was, close. If it was D lowercase s, it would be a small patch of curve, absolutely. And so it's very subtle. This is D uppercase S. What does that mean?
A small patch of surface.
Well, it'll represent a patch of surface, but it actually, it's a normal vector to the surface. And the length of it is the area of the patch of surface. Yeah, so ds is a normal vector to the surface. And look at this, what I'm doing here is I'm taking the dot product of the curl vector with the normal vector to the surface. Let's try to imagine what that could look like. So I'm gonna draw a hemisphere. And let's say, at some point here, here's the normal vector to the surface. So this is gonna be ds. Here's our surface S. Oh, I guess we're calling our surface D now. There's our surface D. There's the normal vector to the surface at that point. But also, so every point on the surface has its own normal vector. And well, I could have chosen the outward one or the inward one. I had to choose an orientation. I picked the outward just to be easy to see. But it doesn't mean it's better. It's just the one I felt like picking. But then also at every point, there's the vector field. And at every, the vector field's got some rotation. So at every point, then there's the vector field has a curl vector. So what's this curl vector doing? Well, let's just say at the same point, the curl vector points in some direction, like maybe the curl vector is going like this. What does it mean for that to be the curl vector at this point? What that means is that's the axis of rotation of the vector field. So what the vector field is doing is it's swimming around that axis of rotation at that point. So there's some rotation going on. Let me see if I can draw it in a way that's convincing. Ooh, that wasn't good at all. It's like this. Does that make sense? There's some rotation going on like that. I really shouldn't keep drawing it all the way up here because it's just happening right here at this point. But I'm just trying to give you the feeling for what's happening. It's rotating like that. So if I think about what's happening with the vector field in that surface at this purple point right here, what's happening is, so here's the surface. Here's the part of the hemisphere, and then here's the normal vector coming like this. Here's the curl vector, so the rotating is happening like this. So I've got the surface, the rotating now, it's sort of punching in and out of the surface. It's rotating like this. So I know that it's a really small image, but maybe if I get closer. Let's pretend this is part of the hemisphere. Then, and then this is the curl vector. This is the normal vector, but the curl vector is angled a little bit. It's not quite the same as the normal vector. So if it's like this, then this rotation is sort of going in and out of the surface. So it's not actually, it's rotating in a plane that's not really parallel to the surface. It's kind of cutting through the surface a little bit. But what happens if I take the dot product of the curl vector and the ds vector? What I'm really doing is I'm asking how much of this rotation, it's like scalar projection. How much of this rotation is happening around the ds vector? To what degree is this? See, this rotation, sure, it's puncturing through and coming out of this blue surface, but still there's some kind of swirling parallel to the blue surface. Let me see. Let me try, maybe I'll mess this picture all the way up, but what do I mean by that? So if, I'm gonna draw this a lot bigger than it deserves to be. So if this swirling around the curl vector would be like this, well, then there's some component of that that's curling around parallel to that's kind of curling around like this. But it's probably a smaller component of it. Can you see the green is meant to look like it's rotating around the ds vector. It's made to look parallel to the surface, whereas the yellow is meant to look like it cuts through. I don't know if it's convincing or not, but that's the idea. So what I'm trying to say is curl of f dot ds, that measures how much of the rotation around the curl vector is sort of propagates to a rotation parallel to or tangent to the surface at that point. So this is a curl f dot ds tells the amount of rotation of the vector field f in a plane that's tangent to the surface. So I'm just gonna say in the surface or tangent to the surface. Some of the rotation is just puncturing through, but that's still gonna stir some points around on the surface. That's the idea. And so how much is it stirring around some points on the surface? Less than it is in the correct direction, but still some. So that's why I made the little green circle smaller than the big yellow circle. Okay, so what's the moral of that? This thing right here. Then what happens when I integrate? Integrating is just adding up. So this is the accumulated amount of rotation added up all over the surface. So this is the accumulated amount of rotation of the vector field f in a direction parallel to the surface. Okay, so let's think about that for a minute. So I've got some surface, whatever it is, and at every point, the vector field is swirling around through it, and that's causing some kind of swirling in the surface, and I'm adding it all up. So maybe there's some positive swirl here, maybe there's some swirling in the other direction here, you know, because the curl vector is going through like this, now the swirling in the other direction, maybe there's no swirling here, and we're gonna add up all the swirling all over the surface to get the net amount of rotation happening. So what's going on with all this swirling? Well, these vector fields are continuous. They have to be if we're taking the derivatives of them. So they're continuous. So all this swirling has to go somewhere, and it's going to propagate to an amount of rotating around the boundary. Can you imagine that? If I'm swirling around all over the middle of the surface, that swirling, if there's sort of a positive amount of swirling, that's going to keep going around the edge of the thing too. So that's going to propagate to, how about pink? Some kind of rotation around the boundary. So that's what Stokes' theorem says, is that it doesn't just relate to it, it's exactly equal to the net amount of rotation around the boundary. We call that the circulation. So rotation around the boundary, that's how well does the vector field line up with the boundary curve? How much does it circulate around the boundary? So that's single integral of f dot dr around the boundary of D. So if I give it its slogan, this is the net circulation of f around the boundary of D. All right, that's pretty heavy stuff that I just talked about. I realize that. But I think to not mention that at all means that you don't get to appreciate the connection between these things. I mean, I think it's a beautiful thing that it exactly works out this way. Somebody figured it out and was able to prove it, this guy Stokes, and we all get to benefit from it. Okay, so this is what the theorem says. This is the formula of the theorem. But by now, we know better than to think that a theorem is just a formula. We know that the theorem has conditions, and we can only use the formula if we've satisfied the conditions. So what are the secret conditions here? Well, let me sort of add these in now. So the conditions to check, first of all, this is going to seem obvious, but since I've seen students struggle with this, I'm just going to, let's see, it'll seem obvious when I call it out. But if I don't call it out, it might not be obvious to you. So let me just call it out. So this only works for a 3D vector field. So need a 3D vector field. For a two-dimensional vector field, actually, you can do the same thing, but I won't be able to tell you today, but turns out the two-dimensional version of Stokes' theorem is just Green's theorem. So Stokes' theorem is a generalization of Green's theorem to 3 dimensions. If you're in 2D, you just use Green's theorem. Okay, so you have to have a 3-dimensional vector field. That's required. But another thing that you need is compatible orientations. So D and boundary of D must have compatible orientations. I haven't told you at all what this means. That's okay. We're going to spend some time talking about compatible orientations in a minute, but let's just, how is that hidden here? Well, that's actually maybe, because I didn't make a big deal out of it, but when I used this notation, boundary of D, I said, well, it's the boundary oriented positively. It's a positively oriented boundary. And that made sense when we were, when we talked about Green's theorem, we had a notion of positive orientation for a boundary. So there was an orientation built into this notation. So this theorem didn't have to be explicit about that because it knew that this notation had it built in. But if I didn't call it out to you, you might not have remembered, oh yeah, there's an orientation question. Well, let's think about this. Anytime you do any integral of a vector field over a surface, over a curve, orientation is always a question, right? Because we might be going over the curve this way, over the curve this way, and that's going to give us a different dot product. We might be going across the surface this way or across the surface this way, and that's going to give us a different dot product. So orientation is going to matter. If the orientations are compatible, then this left-hand side value is going to equal this right-hand side value. But if the orientations are incompatible, it's like we've got like an orientation reversing situation. So these will be related, but not exactly the same. We just have to put a negative sign in. Does that make sense? It's not compatible. We'll do lots of examples of that, but that's just what I mean by compatible. It's still going to be close, but you'll be off by a negative sign if they don't match up. So we'll have to talk about what it means to have compatible orientations, but that's definitely a condition. And then the third condition is also a thing that's really built into the formula, but I've seen students multiple times apply it in the wrong situation, so I'm going to call your attention to it. The double integral has to be of the curl of the vector field F. It can't just be of F. So I want you to check that before you use it so you don't apply it in the wrong situation. So the double integral must be of curl of F, not just F. And look, our double integral here is of curl of F, no problems. Okay, so these are conditions, and then you get to use this awesome formula for Stokes' theorem. You get to swap something that, let's be honest, is pretty daunting. What's it gonna take to do this? 1, parameterize. 2, find RU cross RV so we get DS, right? So we have to find RU, find RV, take the cross product. Oh, we even have to now take the curl of F. Evaluate that at the parameterization, do the dot product, do a double integral. This is a daunting problem right here. I can swap the whole thing with a single line integral because of Stokes' theorem. Okay, so this is going to save us some time and aggravation. All right, so I'm going to talk a little bit more about compatible orientations, but I just said a whole bunch of stuff. I probably just blew everybody away. And let's just take a minute, zen, get centered, see if anybody has any questions, things I should try to explain again.
So you didn't explain how the orientation is compatible yet, right?
Exactly right. We're going to spend probably 5 minutes on that in a minute. Yep, we didn't talk
Okay.
about that pretty.
Okay.
What else is unclear?
What is the boundary of D exactly?
Okay, so the boundary, so if I have a surface, the boundary is like the edge of it. So like in this case, if the surface, so this picture that I tried to draw was an upper hemisphere, so like the top of a sphere. And in that case, then the boundary is the edge. So this pink part is going to be the boundary of the hemisphere. We used that before, like in Green's theorem. I was in the other class. In Green's theorem, well, we're going to talk about this whenever we talk about compatible orientations. So if we remember Green's theorem, let me just start that, compatible orientations. If we recall Green's theorem, we had some curve. Remember, it had to be a simple closed curve in the plane. And then we had the region inside, what we called the region inside D. And then the curve around the edge was called the boundary of D. So it's just the edge of some region. And it doesn't have to be in a plane, turns out. It could be puffed up in 3 space, but still the edge of it is the boundary. What else do we need to talk about? All right, let's talk about compatible orientations. So for Green's theorem, we had an idea of positive orientation. Of the boundary. The reason we could call it positive orientation is, and we didn't have to say anything about compatible, is, you know, we were just stuck in the plane. So there, we didn't really have a choice of normal vector to the plane. There's, well, I guess we could have thought perpendicular that way or that way, but the default is just pick the one coming at you, because, you know, if I had the X and Y axes like that, then the z-axis would be coming towards me. That's sort of the default normal vector to it. So since there was a default, we never had to mention the orientation of D. We just mentioned the orientation of the boundary relative to D. And remember our rules for the positive orientation? It was pretty wordy. The idea was you have the positive orientation if whenever you're walking along the boundary, in the direction of the orientation of the boundary, the region is on your left. Do you remember that rule? Okay, so we're going to generalize that rule for compatible orientations for Stokes' theorem. So positive orientation was when you walk along the boundary in the direction of the orientation. The region is on your left. Okay, so that's for Green's theorem. That's a 2D situation. Let's try to generalize that to 3D in Stokes' theorem. So I'm going to draw, just why not? I'm going to draw the same picture over again. Let's just do a hemisphere. So if I have this hemisphere, so for any shape in 3D, there's no like God-given normal direction. It's not like everybody knows we use the outward normal, or everybody knows we use the inward or the upward or the whatever. It's just sort of arbitrarily chosen. So here's D, and here's the boundary of D. I'll make the boundary, I guess I had it pink before, so I'll make it pink again. Here's the boundary of D. Neither orientation for D, in this case it would be upward or downward, outward or inward, neither of those is bad or is the chosen. We just pick one of them. Once we've chosen one of them, then that decides which direction around the boundary of D is compatible with that one choice. So for example, let's suppose we choose the orientation, the outward orientation, just because it's easier to draw. Let's suppose this is our chosen orientation for D. And the question is, what orientation on the boundary of D is compatible with that orientation? With the chosen orientation of D itself. So here's how you decide. It's really close to the description we gave for Green's theorem or for positive orientation, but now we have to decide on which way is up. We didn't have to decide which way is up. Up for Green's theorem, up in 2D, up is the direction of the z-axis, no problem. But here, now we've chosen up to be the orientation for D. Up is the green direction. So when I'm walking, so I like to pretend that my hand is a little person. So it's my right hand, and I'm walking, and then so this is supposed to be the person's head, okay? And then these are the person's legs, and then this is the person's left hand. Does that make sense? Okay, and so as this thing's walking, how do I know which way to walk? Do I want to walk like this? Do I want to walk like this? Well, I have to orient the head so that the head's pointing up. What counts as up? Up is whatever we chose for the direction for D. So if I walk along the boundary so that my head is in that orientation, which way would I walk so that the region itself, so that D itself is on my left? Would I walk in the direction of the yellow, or would I walk in the direction of the green? So I want to walk
Hello.
in the yellow, absolutely. So the yellow is going to be the direction that's compatible with that chosen orientation for the surface. So the answer is the orientation such that if you walk along the boundary of D in the direction of that orientation, with your head pointing in the direction of the orientation for D, so that's telling you what counts as up for that orientation, pointing in the direction of orientation for D. Well, it's a compatible orientation if the region D is on your left when you do that. That's a lot of words. But we need all that description because there's so much going on. There's so much that we need to do to describe what's happening. Right? This is something we're going to need more practice for sure. We'll have more practice for it, definitely. We're out of class time right now, so it's not going to be right now. But you know, take that, you know, stick that in your pipe and smoke it, right? And we'll think about it next time. We'll try some problems with it. We'll do some practice. For now, the homework for tomorrow. Now you can do 13.7 vector field. And then for Tuesday, we'll be able to do 13.8. And then maybe 13.9, I don't know. But definitely 13.8. So this is sort of foreshadowing what's coming up. All right. Anyone have any last minute questions before we get going?
I have a question.
Okay.
What is like the problem if it doesn't agree, like the boundary D agreeing, the orientation not agreeing with the boundary D and D?
Well, then what that means is that Stokes' theorem wouldn't be literally true. It would be, this would be the negative of that. That's all.
Okay.
Yeah. So yeah, so the orientations agreeing is what makes sure that the signs are going to be compatible as well.
Okay.
Good. What other questions?
Are we having class on Wednesday of next week?
No, because sadly, Wednesday counts as a Friday. So, and in fact, like next Tuesday counts as a Thursday. So if you have, like, I teach a class on Tuesdays only, but it's not going to be next Tuesday because next Tuesday is actually a Thursday. So yeah, next Tuesday is our last class. It's so sad. All right,
Wait,
good
can
to
you
see
say that again?
everybody.
What do you mean by
Yeah, no,
Wednesday?
Tuesday's our last class. Wednesday's class, you go to the classes, you do your Friday schedule. Tuesday, you do our Thursday schedule, but our Tuesday and Thursday classes are at the same time.
Oh, okay, I didn't know that.
Oh, surprise. All right, cool. I'll see everybody tomorrow. Have a good night. Office hours tomorrow at 1:50 if you want to. Bye.
Thank you. Bye.